Okay, happy students. Let me tell you what we're going to learn today. This is Intro to Electricity. This is the last new thing we're learning. We're going to learn about electricity in chapters 18, 19, and 20. You're going to learn about electrical charge. You're going to learn about the force that electrical charges exert on each other. You're going to learn about electrical field, which is the force per unit charge. We're going to learn about voltage, or electrical potential energy per unit charge. We're going to finally learn about Ohm's law, V equals IR, where we use voltage, current, and resistance. And then we're going to make circuits with batteries and resistors and figure out what the equivalent resistance and what the current and voltage is. And it'll be great fun, chapter 20. That's what chapter 20 is. So let's get started. First, our introduction to electricity. Okay? First of all, I need to make sure you're aware of the structure of the atom. This is something everyone here should know. Whoops. Ooh, there goes my pen. I really rolled the wrong way. So, are you okay that your atom consists of a nucleus? And in the nucleus, that's where the protons and neutrons live. And then orbiting the nucleus are your electrons. Your electrons orbit the nucleus. Sometimes they're in the same orbital, sometimes they're in different orbitals. Are you guys okay with that model of the atom?
Yes.
And then secondly, when you have a solid, like a rock or a block of wood or something like that, the nuclei are held in place. I'm making a solid with a very simple crystal structure. It doesn't have to be that way. It can be a lot more random than that. But the point is, the nuclei stay put, and the protons inside the nuclei stay put. So you're never going to have a situation where protons are moving around. The nucleus, which is protons and neutrons, stay where they are at all times. If anything's going to be moving around, it's going to be electrons. Only electrons get to move around. Protons don't. You guys okay with that? Okay, great. Then let's talk about insulator versus conductor. Okay. To do this, I'm going to have to comb my hair. You may have been wondering why I haven't gotten a haircut till now. This is why. This demo I'm about to do. After this, I'm free to get a haircut. Okay. So people way back when, I'm not going to talk about years and people, but just back then, they knew that if you rub two things together, one of them has the ability to exert a force on things around it. Are you seeing this rod? Is it lifting my hair up?
Yeah.
Yes, thank you. It is exerting a force on my hair. Good. Or, for example, here, do you see all these little pieces of paper here on the table? Okay, when I rub this, now it lifts up the paper. Not that much. Come on. Stupid thing. Here, maybe I need to rub it more. These aren't very good atmospheric conditions for me to... There we go. Are you guys okay? It's lifting the paper up. Oh, it's beautiful. Yay. That's pretty cool. Yeah. Look how it lifts it up. Okay. Okay. So, people decided, well, let's go ahead and just rub lots of stuff together and see what we get, okay? And so they found, first of all, there are some things you can rub, and it has that ability to do what we just saw, to attract my hair. These things were called electrics, because it had the ability to exert a force. I don't know where electric comes from, I forget. You just look it up if you want to Google it. What a bad video, what a bad teacher I am. But no one watches these but you guys anyways, who cares? So these are electrics, okay? Whereas there's other things I can rub, like something like this, or something like this. This is a piece of aluminum. I can rubby till the cows come home, and it's not going to do anything. It's not going to track this paper at all. Okay? And so these guys are called non-electrics. Non-electric, because I rubby, nothing. Electric, because I rubby, and it does a lot. Well, it turns out the reason that this guy can be an electric, and I'm not going to go through the evolution of how humankind discovered it, I'm just going to tell you, it's because these molecules, when you give them an electron, it holds on fast to that electron. It says, I love you, electron. I will never let you go. I will never let anyone have you. You must be mine and only mine. So you deposit electrons on this rod, and every molecule that gets an electron holds on tight to it, and it ends up developing a net charge, and then the charge gets to do all the attraction and all that other crazy stuff. Okay? That means if I want to move charge from point A to point B, I don't get to use this guy if I want to move charge from point A to point B, because I put a bunch of charge here at point A, and guess what? All the molecules at point A hold on to them, and those charges don't get to go to point B because they're being held fast by the molecules at point A. That means what this is good for is actually preventing the flow of charge, right? If I have charge here and I don't want the charge to get here, put this guy in the way. And now charge here can't get there because all the charge gets stuck here, and all these guys hold on fast to that charge. Tell me, what is the name for an item like this? I'll give you a hint. It's either an insulator or a conductor. It's an insulator, right? It's an insulator because its molecules hold on tight to the charge. These non-electrics, which there's another name for these non-electrics, what are they made of? Metal. What kind of bonding do the molecules in a metal have? Yeah, metallic bonding. Someone describe, what is metallic bonding? What does that even mean? What's that?
A decentralized sea of electrons.
Okay, a decentralized sea of electrons. Absolutely. Okay? I like to think of this as the perfect condition of mankind, and that is a condition of free love. Right? You've got all the molecules, and you've got all the electrons, and no one owns anybody. Everyone loves everybody. All the electrons can be with whichever molecules they want. All the molecules can be with whichever electrons they want, and they all bond together in a beautiful commune of love. Is that okay with you guys? Because it's okay with me, right? I wish that, well, I shouldn't say it, but wouldn't life be wonderful if we all had that? We just all loved each other. It's beautiful. Okay, great. So the problem is, of course, because electrons aren't owned by any particular, no electron is actually married to any particular molecule, the electrons are free to move. And so, yeah, if I need to get electrons from point A to point B, all I have to do is push them. I push the electrons in that direction, and the electrons just flow because nobody's trying to hold on to them because, hey, it's free, man. It's nature. It's natural. It's natural. Okay, great. So that's insulator versus conductor. I would now like to talk about the tribo-electric series. Remember I told you they rubbed a bunch of stuff together to see what would happen? Well, you do that and you get the tribo-electric series.
Just hit publish for that one.
Wait, just a second. Okay. Processing done. Publish. Thank you. Coming up on the screen, are you seeing a tribo-electric series? So they rub things together, and I'm going to make it scroll down so you're not going to see the word tribo-electric series anymore. But I just want you to see that's what it's called. And also, please do not write this down. This is just for fun. Okay? What's actually happening is something that I've seen some books refer to it as charging by friction, where you're rubbing this wool sock on this PVC pipe, which is a resin. Okay? You're rubbing the wool sock on a PVC pipe, and you are ripping electrons off of the wool and depositing it on the PVC pipe. Okay? So I'm going rubby, 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 and as I rub, I'm physically scuffing or ripping electrons from the wool sock and depositing it on the PVC pipe. You guys okay with that? Okay. But let me ask you this question. What if I were to rub this glass rod with this wool pipe? Now, is this glass rod going to be ripping electrons off the wool sock? Heck no. Yeah, now the glass is going to be the guy losing his electrons, and the wool is the one going to be gaining the electrons. You see what I mean? Okay, so that's the Tribo-electric series. And later on, but here's the thing. But I'm gonna rub the glass rod with the wool sock. And remember when I rubbed this PVC pipe with the wool sock, how it attracted those pieces of paper? Does that mean since this glass rod is going to be charged? Oh, by the way, if something loses electrons, what charge does it acquire? Positive. So you guys okay with that? Before I go on, let me just do a little bit more of this stuff. Here, I've got a sphere, okay? Here's my sphere, and it has a particular mass. And then the next thing I know, that sphere has acquired a charge. That sphere has acquired a charge of positive 5. Tell me, does this sphere weigh more or less than that sphere? He's got charge now. Doesn't that mean he weighs more? Does this guy weigh more or less than that guy?
Less.
Wait, why less? Why would you say less?
You lost the electrons.
Yeah, because the only way you're going to acquire a charge of positive 5 is to lose 5 electrons, right? You're not going to acquire that charge by gaining protons, because remember, protons don't get to move, okay? So yeah, this guy, he acquired the charge because 5 of these electrons exited the sphere, right? They all exited the sphere, and now you've got a charge of positive 5. And by the way, this sphere has a million, billion, trillion, quadrillion charges, right? If it has a charge of positive 5, it doesn't mean it only has 5 protons. You guys okay with that? It just means it has a million, billion, trillion electrons and a million, billion, trillion, and 5 protons. It just means it's got 5 more protons than electrons. You guys okay with that?
Yeah.
Okay, great. Then are you okay that when I rub this glass rod with the wool sock, since the glass rod is losing electrons, what charge is this glass rod acquiring? Yeah, positive. This guy's becoming positively charged. Well, does that mean it's going to repel these pieces of paper, or is it going to still attract the pieces of paper? Remember, this guy attracted the paper. You saw the paper jumping to meet this guy. Does that mean that this positively charged rod is going to repel the paper, or is it going to attract it as well? Well, let's find out. Rubby, 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 rubby. Here we go. Nothing. Oh, come on. Okay, well, can you see it attracted a little? Gosh, come on, you stupid thing. Here. Why am I not getting very good results?
You haven't charged enough.
What's that?
You haven't charged enough.
Yeah, and also look at the Tribo-electric series. Oh, did I mention that the farther apart they are, the more they'll rip electrons, and the closer they are, the less. So do you see that I'm rubbing glass and wool, which are right next to each other in the Tribo-electric series? So I'm not going to get as effective transfer of charge as I would rubbing wool and resin, right? The best would be if I had rabbit's fur and Teflon. That would get me the best results, but I don't happen to have those. Okay, so you know what I'm going to do? I'm going to rub, instead of using glass, do you mind if I use lucite? I might get a little bit better results with lucite. This is a lucite strip. So it's going to be charged positively, rubby, rubby, rubby. And I'm going to demonstrate why it's positive, later this period. But just trust me right now that it's charged positively. And, okay, are you guys okay that it's still attracting? It's just not as good as that, Okay, so that gets me to the next thing I want to talk about, and that is part D. Charged objects always attract neutral objects. Charged objects never, ever, ever repel neutral objects. Charged objects always attract neutral objects, and I'm going to talk about that now. Let me turn this off.
Thank you.
So, okay, here's a meter stick. It is neutral. Okay, here's my my rod here, it's going to be negatively charged. It's ripping electrons off of the wool. Neutral charged attract. You guys okay with that? That it's attracting it? Here, if I want it to stop, I'll just put it on this side. It kind of came away a little bit, so I can. Here we go. So do you believe that charged objects attract neutral objects?
Yes.
Never repel. Okay. Here. How about my lucite? Is my lucite going to attract that meter stick or repel it? Because this is positively charged, not negative like that guy. Hope you see that it attracts it as well. Not as easily. My goodness. Wow, this is not a very good day for static electricity. What the heck? Why is it not moving?
It's broken.
Maybe I need like a way bigger piece of lucite or glass. I don't know why it's not happening for me. Here, let's try this. Come on, baby. Come on, you can do it. Attract. Oh, look at that. It's attracting. Oh, I'm so happy.
Okay.
Okay. Alrighty. Well, let's talk about why neutral always, why charged objects always attract neutral. Okay, here we go. So I've got that big white PVC pipe, and you know it's charged negatively, according to the Tribo-electric series. And then I've got my ruler. Okay, there's my ruler. And it's got a bunch of atoms, and each of these atoms has a nucleus and an electron cloud. Electrons orbiting the nucleus. Under normal circumstances, the electron cloud is completely symmetrical about the nucleus, just forming a circle or whatever it happens to form. But when I put this charged rod close to the ruler, yeah, I'm not going to redraw it. This charged rod is now close to the ruler. Is that going to make the nuclei move? You tell me. Are the nuclei, you know, the positively charged nuclei, are these positively charged nuclei going to move towards this negatively charged rod? Just a second. I'll mark it. Oh no, it's my brother. Wait, what? Lance? I'm teaching. My lunch break is in 22 minutes.
It's important.
Why? What happened?
I don't know.
Yes. Okay. 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 All right then. Okay, I will. Thanks. I'll call you lunch. See you later. Bye-bye. Okay. So, okay. So, what was I saying? Oh, I was asking, does the nucleus get attracted to the rod? How many people say, yeah, that nucleus is going to move toward the rod? Okay, well, here's the thing I want to remind you of. The nucleus doesn't move. It's just stuck there. Nucleus isn't going to do anything. But the electron cloud, I want to remind you, an electron cloud is fungible. An electron cloud is easily deformed. All an electron cloud is a probability function. It just tells you the likelihood of an electron being here versus there versus somewhere else. Okay? So these electron clouds, they're going to deform. When I put this negatively charged rod near the electron cloud, in which direction is that electron cloud going to deform? Say again.
Left.
It's going to be attracted, the electrons will be attracted to the negatively charged rod. You know, I haven't mentioned, are you guys okay that opposites attract? Positives attract negatives, negatives attract positives, but like charges repel, negatives repel negatives, and positives repel positives. So this is a big negatively charged rod, and this is a negatively charged electron cloud. How's the electron cloud going to get deformed?
It's gonna go away from it.
Yeah, it's going to want to get away, right? It's going to, so the electron cloud is going to deform like this. And I won't beat around the bush anymore. The electron cloud is going to get deformed like this. So now you're going to end up with each one of these atoms having a positive side and a negative side. And there's a special name for an atom that has a positive side and a negative side. It starts with D. What do we call these guys? Yeah, you get dipoles, okay? So you're turning all of the atoms in that ruler into dipoles. Okay, and so the negatively charged rod is going to attract the positive side of the dipole. The negatively charged rod is going to repel the negative side of the dipole. But you tell me which, or let me just ask this. Why is it that the attractive force on the positive side of the dipole ends up being greater than the repelling force on the negative side of the dipole? Why? Why would the attractive force of this rod on the positive side of the dipole be greater than the repelling force of this rod on the negative side of the dipole? Shouldn't they be just equal and opposite? Shouldn't there be no net force? Or do you notice something just physically, the difference between where the positive side is and where the negative side is?
The positive is closer to the ruler.
Thank you very much. The positive is closer to the charged rod. Yeah. And so you get attraction, you get a net attractive force. So charged rod attracts neutral object. It attracts neutral object because it induces a dipole in the atoms of the neutral object, and the oppositely charged part of the dipole is closer to the charged object. Here comes my next question. What if I get rid of this negatively charged rod and replace it with a positively charged lucite strip? So now this is positive. How's this guy going to change? How is the electron cloud's deformation going to change? What's that? Thank you very much. It's going to now get deformed towards the left. You see? And now the negative side is closer to the rod, but the rod is positively charged. So again, attraction. You see? So I want you to be aware. That's why charged objects always attract neutral objects. There's static cling. There's no such thing. Have you ever heard of static cling? That used to be a term that was common back when dryers, I don't think the technology on clothes dryers was that good. So because the clothes are going round and round in a clothes dryer, the clothes rubbing on the sides of the clothes dryer was no different than this wool sock rubbing on this rod. So what would happen is your clothes would be done drying and your clothes would be totally staticky. I mean, your clothes would have just a tremendous amount of static charge on them because they acquired it by rubbing the inside of the dryer for 45 minutes, you see? And so your socks would all stick together and your clothing would all be, you'd have to wring it apart and it'd all be staticky cling. Well, that's called static cling, but there's no such thing as static repulsion. You know, there's only static cling because charged objects only attract neutral objects. They don't ever repel neutral objects. Okay, well, I thought you should know that. So I got that. Now it's time to learn about the Coulomb and then to learn by charging by conduction and induction. So let's learn about the Coulomb. And again, what's that? No?
Nothing.
What? Oh, okay.
I was just asking for you another question.
Oh, okay. Was it pertaining to lesson? Oh, ask me. I'm curious.
No.
Are you sure?
It's just about Coulomb's law in chemistry.
Oh, have you guys learned Coulomb's law in chemistry? F equals KQQ over R squared.
No.
Squared?
Maybe.
We did not learn that in chemistry.
Okay. Well then, hey, let's
Something like
do.
charge over.
What's that?
Radius of charge.
Radius over charge?
It's either charge over radius or radius over charge.
Okay.
Something
Charge over radius squared. So it's just the basic inverse square law of electrical attraction and repulsion. Okay, cool. Well, we're going to be even more specific than that. But all I want to tell you now about this guy, Charles Augustine Coulomb, is when he's doing his work with electricity, we didn't even have a name for charge. Like we didn't know anything about charge. We didn't know if charge was continuous, like water, where you can keep pouring out water and you can have the amount of water get smaller and smaller with no end. We didn't know if charge was continuous, or if charge was discrete. You like chicken McNuggets. You know, they didn't know that. And we didn't know how much charge comprised one chicken McNugget of charge. So this guy, Charles Augustine Coulomb, had to just make it up himself. So I said, okay, well, I hereby declare one packet of charge to be the amount of charge on each of these spheres, such that if the spheres are a certain distance apart, they exert a certain force on each other, and I'll call that one packet of charge, one packet of charge. But then later on, because he would never arrogate the term Coulomb for himself, he wouldn't say, and I declare that one Shanghai, one Coulomb. No, he didn't do that. He just said, that's one packet of charge, I guess. But later on, people said, okay, that amount of charge, that when they're held a certain distance apart, exert a certain force on each other, we're going to call that one Coulomb of charge, okay? Well, it turns out that one Coulomb of charge, which is what his packet of charge would be, one Coulomb of charge, ends up equaling approximately 6.24 times 10 to the 18th electrons. Because later on we do the Millikan oil drop experiment and we find out what the smallest unit of charge is. It ends up being an electron. And it turns out that one Coulomb of charge ends up equaling about that many electrons. But the interesting thing is, we do not use this as our conversion factor for charge because the Coulomb came first. So everyone in science prefers to say one electron equals 1.6 times 10 to the negative 19th coulombs. And that's the conversion everyone uses. And that's the conversion I'm going to use in this class because the Coulomb came first. So we define the electron, the amount of electrical charge in terms of the Coulomb. Here's one more thing I want to talk about. Have you ever wondered why electrons are negative and protons are positive? If it's the electrons that are the electrical fluid, if it's the electrons are the ones that flow, where the addition of electrons gives you, charge, and the subtraction of electrons give you charge, why aren't electrons positive? Why is it that if we have an iron ion, Fe plus 3, it gets to be plus 3 because we took away 3 electrons? Usually when you do subtraction, that means you get less. Why would subtraction give you more? Because when you take away 3 electrons, you're subtracting negative 3, and that gives you positive 3. Well, why do we even have negative electrons in the first place? Why not have electrons be positive and let protons be negative? And the answer is because of Ben Franklin. Because what happened with Ben Franklin is he's rubbing glass with silk. And he's rubbing glass with silk, and he's saying, okay, well, my glass has just acquired a positive charge. Okay? But the fact is, his glass did not acquire a positive charge because he deposited a bunch of positive charge on it. His glass acquired a positive charge because it was negatives removed from it. We learned that later. But because we wanted to stick with Ben Franklin's, way of doing things, the only way we could say that a glass rod acquires positive charge is for it to lose electrons and for electrons to have a negative charge. So that's it. Because he was doing glass with silk, we got negative electrons. Okay, let me talk finally about charging by conduction and charging by induction. First of all, here's an electroscope. What's special about an electroscope is that it lets you see the presence of charge. This electroscope consists of just a copper wire that's wound, and then the copper wire passes through this jar, and then I've got a couple of aluminum foil sheets hanging on that copper wire. when this rod goes close to this rod is charged. Do you see what the aluminum foil thingies are doing? Do you see how they're getting apart?
That's crazy.
That's because this rod is negatively charged. Because this rod is negatively charged, when I put it close to the copper wire, what's the you know, a bunch of the free negative charge in that copper wire? What's it going to want to do? What's that just?
Repel.
Yeah, repel. It's going to want to get away from this rod. And the only place for those electrons to go is down into the aluminum foil. Why are the aluminum foil sheets spreading apart?
Because they have the same charge.
Yeah, because they're the same charge, so they're going to repel. Good for you, Gavin. That's exactly right. Here, let me ground this. Okay, so let's say I want to permanently charge this guy. I want to permanently charge it negative. There's two ways to permanently charge something. One way is to just touch it. That's called charging by conduction. Watch this. I'm going to touch it. To keep it. I'm going to touch it. Touchy, touchy, touchy. Okay. And do you notice now it stays apart? That's because some of these negative charges have gone onto the electroscope, and now the electroscope is permanently negatively charged. I can tell that it's negatively charged because I'm going to take this positively charged guy and put it close. And when I put the positively charged guy close, what should happen to those aluminum foil sheets? Do they get farther apart or closer together? I hope you're thinking closer together. Someone describe, why is it those sheets are going to get closer together when I put this positively charged strip next to it?
They're already negatively charged.
Good. So what are all those negatives going to want to do?
They want to attract to the positive.
Yeah, they're going to want to come up to here to be close to this guy. Yeah, want to be close to the positive. So I put it close, and you'll notice it comes closer together. And then it's farther apart. Closer together, farther apart. Closer together, farther apart. Okay, great. Also, that's proof that this is positively charged, because this negatively charged thing, if I get it closer, this negatively charged thing, if I get it closer, they're just going to spread up farther apart, because it's negatively charged. Whereas this guy who's positively charged is going to make them get closer together. Okay. It's not really working that good. I'll chart. Okay. That's one way to charge, by conduction. Two ways to charge a neutral object. Number one, conduction. Touch, charged object to the neutral object. Let me show you another example of charging by conduction. What you see here is a ping pong ball covered in aluminum foil. So it's covered in metal. It is neutral. I'm going to charge this negatively charged rod, and then when I get it close, that neutral object will be attracted to the charged rod. But I want you to see what happens next. Here. Do you see that it's attracted? You guys okay? But I won't let it touch. Okay, you see it's attracted. Great. Okay, well, let's see what happens when it touches. Now, it was attracted. Now, what is it doing?
It's repelling.
Yeah. Do you see now that it's repelling? You guys okay? Why? Why is this object, oh, I don't want it to hit the rod or it'll ground and then it won't do it anymore. But why is it repel? Oh, now it's attracting. Come on, acquire some charge. Is it repelling now? Yeah, it's repelling now. So someone describe, why is it was attracting, but then it touches the rod and now it's repelling? What's going on with that? Yes?
Because it conducted the same charge.
Thank you, because it conducted the same charge. Charging by conduction, and it acquired the same charge as the rod. So now the rod's charged negatively, this charged negatively, and so it's repelling. But I am now going to show you a different type of charging. This is charging by induction. And by induction, you do not touch them. You only get it close. Here we go. Yeah, let me just make sure this guy's grounded. Okay. When I say grounded, I mean by touching it, I'm providing a pathway for charge to go through me to earth, to the ground. And so because earth is so gigantically huge, charge will want to flow from me to the earth. And I'll talk more about that tomorrow. Well, let me show you this. Here, I'm going to get this rod close, and then I'm going to touch the back end of the sphere. Oh, shoot. Here, I got to get this rod out of the way or it's going to make contact. Okay, here I get it close, and then I touch the back end of the sphere. Okay, and now do you see that I'm getting a traction? Here, maybe I should even do it more. Boop. So now I'm getting even more attraction. Okay? Oh shoot, I just grounded it on this rod. Here, let's go. Okay, great. I know that this guy has now acquired a positive charge because it's going to be repelled by this guy. Do you see how this guy, stop rotating. Do you see how this guy is repelling it now? Well, not too much, but I'm repelling it somewhat. Okay. Charging by induction. What I do is I get the neutral object close to the charged rod. Okay? When I do that, because this is metal and the electrons are free to move, all the electrons flee to the far end of that sphere, leaving a net positive charge on this side of the sphere. And then what I do is I ground the far end of the sphere. I touch this with my finger, and I allow a pathway for the electrons to leave the sphere. So these electrons that were on the far end of the sphere leave. Then I remove the ground, and now my sphere is positively charged. Any question or problem on how to charge by induction? If I can put it in words, number one, get the charged rod close to the neutral object. Step one. Step two, ground, that is essentially touch the far end of the neutral object, allowing a pathway for the opposite charge to flow out of your finger, flow through your finger to ground. And then number three, remove the ground. Tell me, which of these two methods results in your neutral object acquiring the same charge as your charged object?
Induction.
Yeah, conduction acquires same charge. And then induction, it acquires the opposite charge. All right. Any questions or has anybody ever taken plastic off of a box and then the plastic just sticks to your hands, sticks to your fingers? Do you guys understand now why that occurs? Hope so. Yeah, it's ripping electrons off the box and then it's attracted to your neutral fingers. Bye-bye.